Good afternoon and welcome to Advanced NMR Spectroscopy course. Today is lecture 4 and I'll speak today about chemical shift. This is a new topic now. Next year, no? It's okay? Okay. So, it is. So let us see what is chemical shift. So what so far we have seen is that the Larmor precession frequency, which you can correlate to the gyromagnetic ratio of the observing nuclei and the applied magnetic field. So omega 0 is the precessional frequency equal to gamma V0. Okay. So this resonance frequency, which sometimes called this precessional frequency, is also as the resonance frequency because it happens during the resonance when the nuclei absorb the radio frequency. So it is influenced. See, if all the hydrogens absorb at the same or the precessional frequency is same, then the NMR has no meaning. Okay, but what is normally seen that this resonance frequency depends on the molecular structure. Okay, so it is influenced by the chemical environment in the molecule. Okay, so chemical environment means there are the bonds. Whether they are in the bond, there are electrons. Okay, so not only the electrons in the chemical bond which is attached to that nucleus, but there are other atoms and neighboring chemical bonds. Those can also influence the resonance frequency. So the value of resonance frequency depends not only independent individual nucleus or that the bond associated with that nucleus, but depends on the full molecular structure. Okay. Here I have shown that suppose if in an NMR machine with applied magnetic field of 1.4 Tesla, the proton resonance supposed to be around 60 megahertz or 60 megahertz. But see, we never see that. We will see the protons resonate nu 0 plus minus delta nu, where delta nu is the spread in resonance frequency. If you remember, I was telling in my last lecture about the offset. So you will see the range of resonance frequency spreading from, there will be some frequencies which are more than nu 0 or the 60 megahertz, some will be less than 60 megahertz, and they will come within a few kilohertz only. Okay, so other nuclei, that is for proton, but other nuclei also follow the same thing, but that effect may not be same. There can be a more or less depending on which nuclei we are observing. So in summary, this effect produced by this different chemical environment of the nuclei which are present in nuclei in the molecule, and this is happening due to the chemical environment. So that's why I call this as a chemical shift. Now here I have shown a proton NMR spectrum of benzyl acetate in a 90 megahertz machine. So 90 megahertz machine means that this represents the radio frequency source used in this machine. So it is at 90 megahertz. Okay, and you see there are three signals. Okay, I will not them call it a singlet or something. There are three signals. You can see that the peak. You can see there is a tall peak, that is PHA. I'm telling that are 5 protons from the phenyl ring is coming, and then there is a peak in between that CH2, call that a B group of protons, and you can see another group of protons C. So we can see that in this molecule there are 3 groups of protons, and they have different chemical environment. One is attached to a carbonyl group. Another the CH2 is attached to a benzene ring as well as a oxygen, and then the remaining protons, the A group protons, are attached to a aromatic benzene ring. Okay, so that, and you can see that they have different positions. They are not coming at the same place. Now the question is that why all these protons are coming at different positions, or why they have different resonance frequencies. Now we will see that what are the reasons for this. Okay. Now, so first one thing is that the shielding of the nuclei. Okay. So when you see, we never see the bare nucleus. So automatically, whenever we talk about a nucleus, there will be a nucleus, and then it is a kind of atom, or in a molecule also, they will be bonded to some other atoms. Okay. So when you apply a magnetic field, okay, so it induces induces the circulation of electrons surrounding the nucleus. Okay, so that produces a magnetic moment in opposite sense to B0. You can see that it has been shown there. The nucleus, the electron is circulating. It is actually it should be shown in 3 dimensions. It should be a spherical in nature, but I'm showing in 2 dimensions, and you can see the magnetic moment which has been produced, and it is opposing the applied magnetic field. So effectively the nucleus is feeling a less magnetic field than what we have applied. So that's why we are calling this as a shielding of nucleus by electrons. Okay, so the local field experienced by the nucleus is now less than B0. So this magnitude of this opposing magnetic moment is proportional to the B0. So this opposing moment actually is not a fixed quantity. Okay, if you increase the field, that also increases, because the circulation sorry, the circulation also increases with increasing magnetic field. So the nucleus thus feels it is called a diamagnetic shielding, and diamagnetic shielding is equal to sigma B0. Sigma is called the shielding constant. So it is a shielding constant into the applied magnetic field. So that's why if you increase the magnetic field, this the opposing magnetic moment also increases. So we can say that the B local means the nucleus which we are observing, or you can call the B effective field equal to B0 into 1 minus sigma. Sigma is called the shielding constant. Okay. So the sigma is the proportionality to electron density. So in the 1s orbital of hydrogen under observation. Okay. So if the electron density in the 1s orbital of hydrogen increases, the sigma will be more, and if it is decreases, sigma will be less. Now we'll see all these things in little bit detail. So that's an instrument. Let us say the instrument, you know, the old instruments, now they could be used as the operating frequency is fixed, and then you vary the magnetic field, or it could be that you can keep the magnetic field constant, and then you vary the radio frequency. Okay, so to bring the nucleus under resonance. Okay. So in the first case, you will see that when the operating frequency is fixed, you have to apply more than the B0 field, so that you have to add little more magnetic field to bring it under resonance to overcome the screening effect. Similarly, if your machine is fixed at a particular magnetic field, then you will see that your nucleus is resonating at lower frequency compared to the calculated value. Okay, so I'll tell you that suppose let us say if you have see, normally the NMR spectrum, actually, okay, so you will see that, let us say this is your magnetic field is your B0 is your that is your B0 is fixed. B0 fixed. Okay. So suppose if there is no shielding, you could have expected, let us say, a particular nucleus should resonate at this position. But because of But as so in NMR, you will see that we plot the NMR from, so this side the nu increases in this direction from right to left. Okay, so because of this, because now the nucleus is experiencing a lower field, so you will see the nucleus will now resonate nu dash. Okay, so this is when in case where your field is fixed. Okay, now the other situation is that you can have your nu zero is fixed. Okay, okay, so let us see if there is no screening. Okay, so you could have expected that, so this is the, see, normally the frequency we show this way, from right to left increases, where the field we show from left to right, it increases. So let us say your this is your this is the field where you this is your, so if there is no screening or shielding, you will see that your signal will appear at B0. But because of the shielding, now you know that it requires a higher field. So you will see that there will be a, you will see that it is coming to a slightly, you require a slightly higher magnetic field, and you can in this particular case you can consider this as a omega 0 is equal to gamma B0, but in this particular case it will be omega dash is equal to gamma. So you will see that this is I can write in terms of nu dash. I think that will be better. This will be your nu dash equal to, so you will be divided by 2 pi. Okay. So in this particular case, so this is your this is your this will be your B0. But what you will see, because you have to now, so this is nothing, this is sigma. Okay, so you have to add additional field that is sigma B0, so that it will resonate into the same nu zero, the fixed frequency. Okay, so that is the thing you have to clear. Okay, so if you have any doubt, you can ask me later on. Okay, now if you, when you come to a molecule, so this is individually fine, but when you come to a molecule, the situation, you will see a complexity. It is not only the atom surrounding electron or the bond connecting to it, but you will see that the neighboring atoms and groups and also surrounding medium, and also there could be weak intramolecular interaction. So those things complicate the situation. Okay, so you will see those things can, sometimes they can be diamagnetic. Some of those effects will be diamagnetic, that means they will increase the shielding, or they can be even paramagnetic, that means they can decrease the shielding. Okay, so they are the final, if you see the sigma or the skinning constant or shielding constant consists of sigma dia, which is coming from the surrounding electron of the nuclei, and skinning constant due to the neighboring atoms and groups and bonds, okay, plus surrounding medium and intra and intermolecular reaction. That gives you the sigma other, and that sigma other can be diamagnetic or it can be paramagnetic, and this sigma dia will be always positive, whereas sigma para will be negative. Okay. Now, okay. So now let us see. So that you now understood what is the screening of the nucleus or the shielding of the nucleus by various electronic arrangement around the nucleus, and also the electrons which are away from it at different atoms and different bonds, and also surrounding medium, all these things that we have seen. Now let us see what are the problems or issues associated with recording a NMR signal. Okay. So what you see that it is virtually impossible to measure absolute frequencies. If you want to measure absolute frequencies, it is impossible to do that with high degree of precision and reproducibility. So that means you measure one time, you go for the next time, you will see a different value, okay, or very close to it. So there is a question of reproducibility. But it is possible to measure frequency difference very precisely. Okay, so frequency difference means you are taking another frequency and then you are subtracting. Okay, for example, so normally this in NMR, the signal frequencies are measured as a difference between the precision frequency of that nuclei and the instrument frequency nu zero. So it is the difference we measure, the delta nu I is equal to nu I minus nu zero. And now you must remember that exactly what we do in rotating frame. What we do in rotating frame, we rotate the frame. So it is nothing but the nu zero. So whenever we see measure the signals, you see the offset signals. Okay, so we never record any signal in megahertz. We always record the signal in kilohertz or hertz. Clear? So that's why here also the rotating frame frequency is very useful. The concept of rotating frame is also very useful. So delta nu I, so we can now measure delta nu I could be measured precisely. There is no doubt about that. But this is not the complete thing. So there could be some issues with the instrument. There could be electronic problem. There could be unavoidable drift, or there could be due to magnetic field fluctuation. There could be also electronic disturbances. Okay, so these pose a problem of reproducibility in the NMR spectrum. So if you record once, the next time you go, there could be a slight change in the magnetic field. Okay, and that will give you a different NMR spectrum. Okay. So so now here I have shown how the NMR spectrum is recorded from left to right. Okay, we'll go to that problem later. Let us see. You see again the NMR of the benzyl acetate, and you see that the peaks have been recorded with respect to the nu I is equal to nu sample minus nu zero, and you see that's why that this methyl is coming to 184.88 hertz only. Okay, because we have now subtracted the machine frequency. You see the CH2B is now 455.50 hertz. Okay, and the phenyl protons are coming in 656.13 hertz. Okay, so now nothing, we are not recording anything in megahertz. Everything we are recording in hertz. This is the advantage of subtracting the machine frequency from the sample frequency or some nucleus resonance frequency. Okay. Now the second issue is that the drifting, because of the magnetic field changes and other electronic component issues in the machine. So to overcome that drifting in NMR scale position, a reference compound is added to sample solution. Okay, so here we are putting a reference sample whose delta nu I is fixed at 0. Again, delta nu I is the new reference new I due to the reference sample minus the new machine. Okay, and that we are keeping at fixed at 0. Okay, and with respect to that, okay, we are giving the frequency of your sample nuclei. Okay, so see, now if there is a drifting, it will drift your sample signal also, reference signal also. Okay, so the difference between them will remain constant. So we tell that delta nu I equal to del nu I minus del nu reference. Okay, so that uncertainty, so we have removed the uncertainty of precisely detecting NMR frequency, and then uncertainty of magnetic field and electronic component noise by putting a reference. So this, we arbitrarily assign this reference signal to value of 0, but you can take any value. See, most of the time we take as 0, but you can assign it to any other frequency. See, nowadays we don't use TMS as a reference, because TMS is being used earlier, and we used to take all these 12 proton signals to 0. But nowadays people even do referencing of the residual chloroform in CDCl3, and that is put at 7.26. So not necessarily, but that 7.26 is coming with reference to TMS. Okay, so ultimately you are referencing all the spectra with respect to TMS. Okay, but you can use any other reference, I mean to say that. Okay, and then measure the frequencies in a hertz downfield. So if it is downfield, I have already shown you that it will be towards the left of your spectrum, and upfield will be towards the right side of the reference signal. Okay, and also it is very important, the reference signal, what you are measuring, should also come from the same isotope of the reference chemical. Okay, suppose you are measuring proton, so it should come from the proton signal of the reference compound. Similarly, if you are recording carbon-13, it should come from the carbon-13 nuclei of the reference sample. Okay, so here I have shown a list of references commonly used in NMR spectroscopy. You see, for proton NMR, mostly it is the tetramethylsilane, and you get 12 protons, single line, singlet, and we put the frequency at 0 Hz. Similarly, the sample is water soluble, we use again a silicon derivative. It is a 3-trimethylsilyl propane sulfonic acid sodium salt, and again the 9 hydrogens of TMS, the trimethylsilyl group is put frequency as 0. Similarly, for carbon and all other things have been given. Okay, for the last one is for phosphorus. I'm telling this as a external. See, in all other cases, where I have not mentioned as external, we put that chemical, the reference compound, into the solution of the compound in whatever solvent you are using. But when we call this is external, we are not putting this reference in the solution of the sample, but what we are doing, we are putting in a capillary tube, and capillary tube is put inside the NMR tube. So there is no direct mixing of the reference with the sample. Okay, that part is clear. So that's why it is called external, but still it will record the NMR. So what so far we have done, we have removed the uncertainty related to absolute frequency by introducing the frequency difference. Okay, and then we remove the drifting due to electronics and a magnetic field by using a reference. Now the third problem comes, that this delta nu I will vary from machine to machine. It will not be constant in all machines. Suppose if you record in 60 megahertz, if you record the same NMR in 500 megahertz, you will see you're getting a different delta nu I values. Okay, because we know that the precessional frequency depends on the applied magnetic field, and the difference is precessional frequency is also depends on the applied field. I'll show you here. It is let us say let us say you are using a machine. Let us say this is your 0 and you are 1 in some this is, let us say, coming in 100 hertz in a 100 megahertz machine. Okay, so if you record the same, you will see that the peak is coming now at 200 hertz. So let us say this is 100, 200, 300, 400 and 500. This is in hertz. Okay, so you will see that when you go for the 200, so you will see it is coming at 200 hertz, 200 hertz in a 200 megahertz machine. If you record this in a 500 megahertz, same peak you will get in 500 hertz in a 500 megahertz. Okay, so it becomes a machine dependent property. So that will be difficult. So it will be always you have to tell which machine you have recorded the NMR. Although when you report a NMR spectra, you always mention that, but you can see that now if you record in this hertz unit, they will not be, they will not look always the same time. You will see the difference. Okay, so how to remove that thing? So to avoid this, a new scale called delta scale has been introduced. So what is delta scale? I think I have shown here that delta is equal to delta scale for a particular nuclear delta I is equal to delta nu I minus delta nu reference. So I have already told what is delta nu I. Delta nu I is nothing but nu I minus nu 0, the machine frequency. Delta nu reference is nu reference minus nu 0, the difference between the reference sample frequency and machine frequency. Okay, and nu 0 is the machine frequency, and we are multiplying it with a 10 to the power 6, and everything, all these things are in hertz unit. Okay, so otherwise, so that why we are multiplying this is with 10 to the power minus 6, just to get a single, other everything will come in 10 to the power minus 6, because the nu 0 is 10 to the power 6 hertz. Okay, so if you see this delta scale right now is dimensionless, there is no unit for this, but this ppm, we sometimes tell this is in ppm because we are multiplying this with a factor of 10 to the power 6. Okay, okay, so now let us see what changes happen when we moved from frequency to delta scale. So this will now now this will be your delta scale. So we put this as a 0. Let us say put as -1, -2, 1, 2, 3, 4, 5, 6. Okay, now if you go for a, let us say, 60 megahertz machine, if you see the frequency of this will be 0, this will be -60, this will be -120. These are in hertz units. This will be 60, this will be 120, 180, 240, 300 and 360. Now you go to a 100 megahertz machine. So this will be again 0, it will remain 0 because we deliberately kept it 0. So this will be -100 hertz, -120, sorry, -200 hertz. And this will be your 100, 200, 300, 400, 500 and 600. You go to 500 megahertz, so it will be 3000, 2500, 2000, 1500, 1000, 500, 0, -500, minus 1000. Okay, so now you see that if you any signal which is coming in a machine with 60 megahertz, let us say one signal was coming at 1.5 ppm, delta is equal to 1.5 ppm. It will remain at 1.5 ppm for all machine because we have taken care of by this formula. So that's why if you keep in frequency scale, they will be different. Okay, in 60 megahertz, let us say it is coming at 90 hertz, it will 100 megahertz, it will come at 150 hertz, 200 it will come at you can see 300 hertz, and 500 will come at 750 hertz. Okay, but in delta scale they will remain constant. Okay, so moving from all these frequency scale to ppm scale has the advantage. Now you see this is a generally NMR spectrum, how it looks like. So TMS comes at 0, and all these which are less screened or less shielded comes left side. We call them low field. We call they are in high frequency, and you will see these comes from the most of the organic compounds. And if you go to the right side, you will see they are the more shielded or more screened than TMS. That right hand side is called the high field. They have the low frequency, and you will see that thing in many metal hydrides and some organometallic complexes. We will see when you go to the next those topics later. Clear? Okay, so now we'll see some effect of symmetry on NMR spectrum. Let us see. Let us say you have a structure, and how we'll know that whether this particular nuclei will be distinguishable in NMR spectrum. So you will see sometimes they will be distinguishable, and sometimes they will not be distinguishable. So let us see when they will be distinguishable, when they will be not. Okay, so to test the distinguishability, it is based on the symmetry relations among the nuclei. Okay, the symmetry things you must have studied in group theory during your chemistry courses. So there are three principal types of symmetry elements. One is called the axis, planes, and center. Okay, so the definition of axis is that a n-fold axis of symmetry is an imaginary axis which is passing through the center of the object. Okay, rotation around this axis by 360 by n leaves the object indistinguishable from the original. I can see the methyl chloride, there is a C3 axis, you rotate by 120 degree, you will see there is no, you cannot distinguish. Okay. Now a plane of symmetry is an imaginary plane passing through the center of the object, dividing the object in such a way that the half of the object on one side of the plane in the mirror image is the mirror image of the half of the other side. You can see the sigma b which is passing through that the center of the molecule. Now you can see that these hydrogens which is below the plane and the above the plane are not distinguishable. And then there are molecules also. Those are called the center of symmetry. So you can see the example when every atom in this structure, if you see those two hydrogens, okay, so an indistinguishable companion. See these two hydrogens, they have indistinguishable companion. So these two hydrogens are connected, okay, and located at the same distance from the center along a line through the center connecting the atom. You can see both the chlorines and both the hydrogens. Another example is this. You can see these two hydrogens are also equally away from the center point of the molecule. Similarly, the two chlorines and the two bromines. In such cases also, so these we call these either by axes, planes, or centers. Okay, these nuclei are called chemically equivalent nuclei, and if the nuclei are chemically equivalent, they are indistinguishable by NMR. Okay. So all chemically equivalent nuclei are indistinguishable by NMR. They are also called isochronous. means they have the same resonance frequency. Hence, they have the same chemical shift. If the resonance frequency is same, they will have the same chemical shift. Now I'll give some example. Let us say this benzene. You should be able to find out there are 6 hydrogens. So you can see very quickly, you can see there is a C6. So all hydrogens are equivalent. Okay, there are also molecular planes. So you first see whether there is any CN. So this is having a C6. So all the hydrogens are equivalent and they will come in the same position. Okay. For example, you take this. Diethyl ether. You can see there is also a C2. There is also sigma planes. So you will see these CH2s and these two CH2s, they are chemically equivalent. These CH3 and these CH3 are chemically equivalent. Okay. So they will see that these two methyls, they will come as at the same place. Similarly, these two CH2 methylines will also come at the same place. Okay. So you can call them as a group of A group, B group, A group, B group. Now there will be let us see a molecule. See, this molecule do not have a axis of symmetry. Okay, but it has a plane of symmetry. You can see the plane of this benzene ring plane. Okay, there is a plane of symmetry. Okay, so then also you will see these two hydrogens, this one and this one, they will be chemically equivalent and they will come to the they will have the same chemical shift. Okay, then you can see another little bit of different type of molecule I'll draw. Let us say diketopiperazine. You see, so there is a center of symmetry here. This methyl and this methyl, they are equally, they are connected by the same line and they are equally away from the center. See, this hydrogen and this hydrogen are also, they have a symmetry, the center of symmetry. This hydrogen and this hydrogen. So you will see that these two methyls, they are also coming at the same place. These two hydrogens are also, they have the same chemical shift, and these two hydrogens also, they have the same chemical shift. Okay, so they have the center of symmetry. Now we'll take another example where the conformation and symmetry is very important. We'll see the toluene. Now, if you take a molecule slightly, so now the toluene is nothing but a methyl group is attached to the benzene ring, and you see that it can have two conformations. And so, in one conformation, the molecular plane of the aromatic ring is the plane of symmetry, and other is the molecular plane perpendicular. And if you see in the case of, let us say, structure A, the left hand side structure, if you see that the two orthoprotons of the benzene ring are chemically equivalent, two metaprotons are equivalent. Similarly, two HA of the methyl are equivalent, but they are different from the HB. Now, this is one conformation. The other conformation, if you see, in the other conformation, if you see the one HB is in the plane of the ring, and HA, two H's are, one is below the plane and another is above the plane. And you see, now you will see that two orthoprotons are not equivalent. Two metaprotons are also not equivalent. Okay, so in the first case, the structure A, you will see 5,1H signals. Similarly, you can see in carbon also you will see 5,13C signals. But in case of structure B, because of this, you will see 1H signals and 7,13C signals if these are the two conformations are there. But if you see in reality, you will see that all three hydrogens of methyl group appear at the same place. You will get a single line for methyls. Similarly, you will see two orthoprotons are coming together, two metaprotons are coming together, and you will see the two orthocarbons, two metacarbons are also coming at the same position as they are equivalent. So this is because the rate at which the phenyl carbon, the benzene ring carbon and the methyl carbon, single bond, that it rotates. Okay, so and the rotation of this bond is extremely fast in NMR time scale. We will come to this NMR time scale when we will see the dynamics in NMR spectra. Okay, but timing, you just remember that this rotates very fast. Okay, in NMR time scale, so you are getting a time average spectrum. Okay, so the methyl group behaves as it is a C3 axis. Okay, so generating all three, so it is a localized C3 axis, so it is making all the three hydrogens equivalent, and that in turn making both the ortho hydrogens, orthocarbons are equivalent. Similarly, both the meta hydrogens are equivalent, meta carbons are equivalent. Okay, but let us say if we can reduce this interconversion of conformants is slow. Okay, in a NMR time scale, we will see multiple signals from the methyl group as well as the aromatic proton, as I shown you from the conformers. Okay, now we will see another type of the nuclei, which we call them as a homotopic. So when we call that homotopic, when the nuclei are related to each other by a CN axis where n is greater than 1, we call them homotopic. We have already told you the methyl chloride, methylene chloride, they are called homotopic because they are related by C3 axis or C2 axis. So when the two nuclei is equivalent by virtue of a sigma plane, if you remember, I gave you show you one example where there is no CN axis, but there is only sigma plane. They are called enantiotopic. Okay, and so they also give one signal. This is, you can see the molecule. There is no CN axis, but there is a sigma plane. How we will find out that? You can see that if you substitute each hydrogen separately, you will get get the same molecule, but you will get the enantiomer. So left side, you can see that those two structures are mirror image related. Similarly, you can see the structure in the left hand side. These two hydrogens. Okay, these two hydrogens are also enantiotopic hydrogen. Okay, and these two methyls are also enantiotopic methyl group. That means if you replace this hydrogen with any other group, you will get a enantiomer. Similarly, you replace or react one methyl group selectively, you will get also a enantiomer. So these two methyl, not necessarily it has to be hydrogen. Even the groups like methyl or phenyl or any group, they can be also enantiotopic groups. Now there is another situation when when this group, you see this CH2, this CH2 group is attached to a carbon which is chiral. That means all the substituents are different. Then you will see that these two hydrogens are not chemically equivalent. This hydrogen and this hydrogen are not chemically same. Okay, so they are called diastereotopic hydrogen. Diastereotopic hydrogen is coming from the word that if you replace this hydrogen with any other group or even an isotope, you will get one diastereoisomer. If you replace this hydrogen with a group or any other atom or even an isotope of hydrogen, you will get the other diastereoisomer, second diastereoisomer. So these two hydrogens, so the homotopic and enantiotopic groups, they are chemically equivalent, but diastereotopic groups are not chemically equivalent. So diastereotopic groups resonate at different resonant frequency and they will have different chemical shifts. Okay, I'll skip this. Okay, now there is one thing is called the accidental equivalence. Okay, so these nuclei, you will see some of the compounds, na, you are getting only one signal that is not due to the symmetry. Okay, but somehow their precessional frequencies are same. For example, the cyclopentanone, you will see that if you record this thing in a 60 megahertz machine, you are getting only one line. Similarly, if you take this propine in record in 60 megahertz, you will get only a single line. That does not mean that they are chemically equivalent. If you record the NMR in a higher field NMR machine, you will see that now the protons will be coming in a different position. So not necessarily that's why these are called the accidental equivalence. And accidental equivalence can be resolved using a different machine. Okay, now we will see quickly what are the origins of these proton chemical shifts. So there are one thing is that that is the local diamagnetic contribution of the electron cloud around the proton. So that gives you always a local diamagnetic field because of the circulation of the electron. I have told you it reduces the effect of the applied field. So that is called a sigma local dia. The other could be that the influences coming from the surrounding atoms and groups. Atoms and groups means atoms and bonds in the molecule. So we call that as a sigma prime, and sigma prime they will have the again a diamagnetic effect due to inductive as well as mesomeric effect. We will tell that after in the maybe next slide or next to next. So what is inductive and mesomeric effect? And then you will see that there will be electronic circulation induced by this applied magnetic field in the neighboring atoms, okay, or neighboring bonds. Okay, so they will give you rise to magnetic moment, and that will give you a secondary magnetic field. But this secondary magnetic field could be diamagnetic. That means it can reduce the effect of applied magnetic field, or it can be paramagnetic. So it can reduce the effect or enhance the effect of applied magnetic field. Okay, so in totality you have to see. So if combining these two, you will see a effective field faced by the or experiencing by a proton which you are observing in the NMR. Okay, so beside that, there could be other effect like electric field. There will be effect of van der Waals effect, and then there will be a surrounding medium effect. Okay, they also influence the proton chemical shift, and we will see some of example of various such effects and how they change the chemical shift of the proton. So any change in proton screening, that is we call that delta sigma, consists of several terms like it is made up of sigma local diamagnetic, that is just surrounding that proton. Then you will have the magnetic, that is called the due to the magnetic effect of the or magnetic moments from the bonds and the atoms. And then you will see the delta sigma due to electric field. Then you will see the delta sigma due to van der Waals effect, and then you will see due to the solvent or surrounding effect. Okay. The most important thing in NMR so far, whatever we will be discussing, that in solution, the recorded chemical shifts are weighted average of all possible conformations of a molecule which are in dynamic equilibrium. Please remember this, that whatever we are recording is not, although we are drawing a structure of a particular conformation, but the chemical shifts are not due to that conformation. It is coming from the all conformations and their weightage average. See, all the conformation will not have the same probability. So they will have a different. Okay. So it is coming from that. Okay, and also the molecule can orient in all possible. See, if you consider any conformer, any conformation, they can orient around on the so they can be along the they can orient along the applied field, they can orient against the applied field. So we are considering all those things. So it is the weightage average of all possible conformation of a molecule which are in dynamic equilibrium. We are calling it dynamic equilibrium. We'll see that because that part is coming from the again the NMR time scale. We'll discuss later on. But timing consider that these are very fast processes. okay, compared to the NMR time scale, and all possible orientation of each of these conformation with respect to the direction of the applied magnetic field. So here we see in a NMR in solution, the summary is that in solution we see the average spectrum. Okay. Now let us see how the electron density of proton affects around the proton affects the chemical shift. Okay. So if you take a consider a hydrogen atom, it is solely coming from the electron the density of the hydrogen, and it is solely a diamagnetic effect. Okay. But when you attach to any other atom, the electronegativity depends on depending on the electronegativity of that element. If the electronegativity is higher, it will try to drag the electron, so the electron density around hydrogen will be decreasing, and so the spinning constant also will fall, and in the order of electronegativity, which I have shown here for HF less than HCl, less than HBr, less than HI. Okay. And depending on the electronegativity, how the chemical shift value of the methyl protons in methyl chloride, methyl bromide, methyl iodide, and methane values that I have shown here, and also their Pauling electronegativities. Okay. Now, in case of ethyl halides, now we have added a one more CH3 group. Okay. Instead of that was CH3F, we are putting as a CH3CH2F. Now, what you will see that in ethyl halides, the chemical shift of CH2 group. Okay, the CH2 group actually it follows the electronegativity. You will see depending on the electronegativity, the chemical shift you can correlate. But you will see in case of methyl group, say they do not follow the observed electronegativity effect. Okay, you will see the methyl group of ethyl bromide is having the highest delta value. It is more than iodide, even it is more than chloride and fluoride. So that means that you cannot explain the chemical shift values only basis of only on the electronegativities or the electronegativities or the electron drawing power of the substituent. But there is also now you see the magnetic anisotropy effect of the CH group. Okay, so there are now these surrounding groups like CH bonds, and you have the CX bond. They actually change the magnetic field experienced by the methyl group, and that depends on those bonds also as well as groups and their orientation, and there are so many things. Okay, so we'll see that now. I have told you the several parameters, that the delta sigma, this magnetic effect is very important. I'll take just 5 minutes, Palla. Started late, na? Okay. Okay, so now if you see that electron density, you can explain very nicely if you see the organometallic compounds where the metal is directly bonded to methyl. For example, like metal, where I have shown this order, mercury, tin, cadmium, zinc, aluminium, magnesium, and lithium. You see that they are the polarity of these. Like for mercury, the bond is 9% the polar, whereas for lithium it is 43% polar, and you will see the delta CH3 values decreases accordingly. You will see the lithium, methyl lithium will have the lowest frequency, or you will see the higher minus delta values, okay, compared to mercury. Now, in case of these molecules, now they are all three molecules are aromatic. The benzene, which we know that it comes around 7.27 ppm, but if you see, this is also aromatic. But now you see because of this positive charge, okay, the electron density around all these hydrogens are equivalent. Okay, that I have already explained to you. Okay, now you see the electron, because of this positive charge, the electron density around in this all these carbons attaching the hydrogens are now reduced compared to benzene. So that's why you can see the chemical shift is now delta value has increased. In this case of this is a 5-member cyclopentadienyl and pentadienyl anion. This is also aromatic. Now you see the electron density on the carbons are increased, so that also influence the electron density around the hydrogen, and you can see the chemical delta value is now decreased compared to benzene. Okay, so we can see an inverse linear correlation between the pi electron density and the chemical shift of the protons on these cases. Okay, so this can be considered as the partial charge on pz orbital of the carbon, decrease or increase electron density on 1s orbital of the hydrogen. Similarly, you can see the resonance effect of how the orthoprotons and paraprotons are chemical shifts are affected by putting a electron donating group or a electron withdrawing group. For example, the benzene comes at 7.27 ppm, but if you take the cyanobenzene, you see the orthoproton is now deshielded by 7 because of the electron withdrawing effect. Ortho and para both are deshielded, whereas the meta has a very little effect on the meta. In case of methoxybenzene, you see the ortho and paraprotons are shielded. Now these protons have uphill shifted, and the metaproton is very slightly affected. Similarly, this you can see the electron density at the proton. You see this benzyl lithium. You see benzyl lithium. I'll draw the resonance structure because I have not drawn for others, so I'll stop here after this. So you can think that CH2 minus. So you can think that this is a negative charge. So if you draw the resonance structure, you will see that. See these are the orthoproton, so you can see the orthoproton and paraproton. They are the electron density has increased due to the resonance. That's why their chemical shifts are now the protons are more shielded, and the chemical shifts have moved from 7.21 to 6.09, 7.27 to 6.09. Similarly, in this case, in the second case, you see that this is now a positive charge. So the now positive charge will be, instead of negative charge, here you will have the ortho position positive charge, para position positive charge, and this ortho position also positive charge, and you will see there is a now decrease in electron density around the hydrogen. So it is deshielded, and the chemical value has now, delta value has now increased with a very little effect in the meta compared to the ortho and para. This is due to the inductive effect. So you are seeing both. You are seeing both inductive effect as well as the resonance. But in case of, you see this tetramethyl trimethyl methyl anilinium salt. In this case, you see only the inductive effects. Okay, so almost see all the protons are equally affected. See, this is 7.98, this is 7.66, this is 7.60. Very close, because this nitrogen cannot undergo a resonance, because if you do that, draw that resonance structure, it will be a which is not possible, because nitrogen cannot become pentavalent. Okay, so that's why this is a molecule where you see only due to inductive effect. Okay, whereas here you can see due to both inductive and mesomeric effect. So again, the very similar examples, I will not go into the details. Okay, So here you can see if you take the isopropyl cation, you see the proton chemical shift is at 13.5 ppm, and the methyl groups are also significantly downpilled. Okay, same for tertiary butyl cation comes at 4.35. Normally methyl groups come around 1.2. Okay, because of the significant decrease of the electron density around the hydrogen due to this positive charge. Now the alkyl lithiums, you can see the delta hydrogens of methyl groups comes at minus 1.3 ppm. Okay, but you see that in case of this ethyl lithia, the chemical shift of delta hydrogen of this methyl group comes at 1.33. Again, the magnetic anisotropic effect, we will explain this in later on, that is now playing. Okay, it is not only the inductive effect. Similarly, this is the last ones. So charge density, you can see that alkenes also, if you see the just ethylene, the chemical shift is 5.9. We'll explain why this is 5 point later on. But if you put a OI as an electron donating group like methoxy group, you see that now if you consider the resonance, we are putting a more electron density on this carbon. Okay, so that influences the chemical state of this thing. Now you can see they are now uphill shifted, or they are more shielded compared to the ethylene. Similarly, if you put a electron withdrawing group, okay, like a COCH3 group, you will see that the electron density is taken away from this, and you are generating in a resonance structure, you are generating a cation, and you can see now that these two hydrogens are highly deshielded, and they come at much lower chemical shift position than the ethylene. So I'll stop here. If you have any doubt, you can ask me in the next lecture, okay, or you can send email. Not only this lecture, all previous lectures. Okay, thank you. Share it.
Unmute paper cover and ask if any question you can ask.
You can ask me if you have any doubt.
नोटिस को और एक बार पेस्ट करके दे दो। श्योर, जो नोटिस बनाए थे ना।
ঠিক আছে, পাল্লা কি ফাস্ট ছিল না স্লো ছিল?
একদম পারফেক্ট আছে।
এর চেয়ে স্লো করলে হবে না,
এটা ঠিক আছে, একদম পারফেক্ট স্পিড আছে।
আমি সেই হিসাবে বানিয়েছি যে আজকে এটা শেষ
জন্য नोटिस है ऑलरेडी पेस्टेड ना।
आप एक बार बोल भी दो यही नोटिस। Hello everyone. See, from 27th of February, from Monday, all the lectures will be now from 4 p.m. Okay, so please join at 4 p.m. All lectures, Monday, Tuesday, Thursday, and Friday, your lectures will be from 4 p.m. Okay, so please join at 4 p.m. because 5:30 is becoming a little bit odd for many of you. That's why you have changed it. Okay? And if you have any other issues, please let us know.
Yeah, one email has been sent to all the participants, so please check your email. Okay, and this revised timetable will be uploaded in our Vidya site, so that also you can follow. But remember that we are planning to change it to 4 o'clock to make the operational procedures simpler. Okay.
And there is no any change in the dates.
Remember, no change in the dates. Dates remain the same, only time. Time slot is changed to 4 to 5 for all the
lectures. All the lectures.
Okay, please note it.
Hmm.